You know, when you think about data today, you probably picture the cloud. It's this like invisible, weightless realm of zeros and ones just floating around in some sterile, climate-controlled server farm somewhere.
Right, yeah. We carry around this deep-seated assumption that, well, that all critical measurements in our modern infrastructure are just happening via microchips and fiber optic cables.
Exactly. Like you pull out your phone, you look at a dashboard, and you expect your information to be entirely digital, completely silent and absolutely instantaneous.
Yeah, the physical world has been uh, completely abstracted away into software for most of us.
It really has. But then, okay, imagine you step out of a truck into the freezing, wind-whipped wilderness of northern Alberta. I mean, you are miles from the nearest paved road, let alone a reliable power grid.
Oh, absolutely nowhere.
Right. And you walk up to this massive, humming steel pipeline. You open up a frosted metal cabinet, and that entire digital illusion just completely shatters.
Because you're looking at a totally different kind of data storage.
Exactly. One that relies on gears, ticking springs, physical levers, and the smell of actual wet ink.
Yeah, you are stepping into the rugged, unyielding, and surprisingly precise analog world of chart recorders.
Welcome to a brand new deep dive. Today, we're taking a really fascinating look at these unsung heroes of industrial history and honestly, modern remote engineering too.
Yeah, they are incredible devices.
They really are. And our grounding material for this deep dive is this wonderfully detailed instructor training manual from the Northern Alberta Institute of Technology, NAIT, and the Southern Alberta Institute of Technology, SAIT, all about chart recorders.
And our mission today is to kind of step past that modern microchip-obsessed world you were just talking about.
Right.
We want to show the brilliant, intricate mechanical engineering inside these heavy steel cabinets. We're going to explore how pure physical forces, like the roaring pressure of natural gas, are translated directly into permanent paper records.
And why these purely analog machines are, still trusted out in the harshest field conditions even today. Okay, let's unpack this. Because before we can understand how massive industrial pressures or flowing gases are actually measured, we really need to understand the physical canvas of the chart recorder itself and, well, the tools that do the drawing.
The hardware itself, right?
Right. I like to think of a circular chart recorder as a kind of sophisticated, reverse record player.
Oh, a reverse record player. That's actually a really helpful way to visualize it.
Because instead of a stationary needle reading a microscopic groove on a spinning vinyl disc to generate music, you have these delicate ink-filled pens.
Right, and they're moving back and forth.
Exactly, drawing a permanent historical record onto a slowly rotating circular paper disc.
And the heart of that entire operation, the thing that makes it work, is the chart drive motor.
Okay.
This is the mechanism responsible for driving the paper chart past those pens at a completely steady, perfectly reliable rate.
Which is crucial, obviously.
Very crucial. And what's fascinating here is the historical genius of the older spring wound mechanisms that are detailed in the manual.
Which makes total sense when you consider the environment, right? I mean, you can't exactly run an extension cord through 50 miles of Canadian tundra just to plug this thing into a wall outlet.
No, absolutely not. In those remote wilderness settings, a stable power supply was often completely unavailable.
So what do they do?
Well, engineers relied on spring wound motors. So a technician would literally open the cabinet and physically wind it up with a key.
Wait, really? Like an old grandfather clock?
Exactly like an old grandfather clock.
Yeah.
That stored mechanical energy would slowly release, allowing the device to operate completely autonomously for days or, even weeks at a time.
That is wild.
The manual actually notes that the motor part numbers were specifically tied to their duration. So you install, say, a 12-hour motor or a 24-hour, a 7-day, or an 8-day motor, depending on how often a human could actually trek out to that location.
Wow, pure mechanical energy, keeping perfect time and securing the data. But, I mean, a spinning piece of blank paper is useless without the data itself, right? The manual highlights the Barton Model 202E recorder, and I'm just trying to figure out how you get the pipeline's actual conditions onto that paper without a single electrical wire running between them.
It's all physical forces.
Right, but for instance, temperature. How exactly do you record the temperature of the gas flowing inside a thick steel pipe, purely mechanically?
So engineers achieve this using what the manual calls a filled system.
Okay, filled with what?
Well, imagine a completely sealed, fluid-filled temperature measurement assembly.
So it's literally just a closed loop of actual fluid pushing against a mechanical lever.
That is the basic physics of it, yeah. You have a middle sensing bulb that sits physically inside the pipeline, so it's constantly exposed to the temperature of the flowing gas.
Right.
As that temperature changes, the specialized fluid that's completely sealed inside that bulb either expands when it gets hot or it contracts when it gets cold.
Oh, I see.
And this expansion or contraction changes the internal pressure within the attached capillary tube. That physical pressure change travels all the way up the tube right into the recorder cabinet, where it physically pushes the linkage connected to the green temperature pin.
Wait, hold on. If you have a tube of fluid running from a hot sensing bulb inside the pipe, out through the freezing winter air and all the way into the cabinet, wouldn't the ambient weather outside the pipe affect the fluid in the tube too?
Oh, absolutely.
Because if it's like negative 40 degrees outside, that long capillary tube is freezing, which should contract the fluid and completely ruin the reading of what's happening inside the pipe.
You've identified the exact flaw that engineers had to overcome.
Oh, okay.
And their solution is incredibly clever. The manual points out a specific feature on these recorders called the ambient compensation capillary.
Ambient compensation capillary. That sounds like a sci-fi term. How does that physically work?
Well, its job is entirely practical. You only want to record the temperature at the actual sensing bulb inside the process, right?
Yeah.
You do not want the ambient air temperature surrounding the long connecting wire, the capillary, altering your data. So the engineers run a second identical capillary tube right alongside the main measurement one.
A second tube.
Yeah. But the second tube isn't connected to the sensing bulb in the pipe. It is only exposed to the outside weather.
Oh, I think I see where this is going.
Right. So inside the cabinet, this ambient compensation capillary is rigged to actively push back against the main capillary's mechanism. It mechanically cancels out any pressure changes caused by the outside environment.
That is amazing.
It ensures the green pen only moves based on what the bulb inside the pipe is actually feeling.
It is physical problem solving at its absolute finest. Literally two tubes fighting each other to isolate the true data.
Exactly. And to keep all this data readable for the operator who opens that cabinet, the disposable pens are universally color-coded.
Right. On that Barton Model 22E, you have the green pen we just mentioned for temperature, a red pen for differential pressure, and a blue pen for static pressure.
Yeah. It creates a standardized visual language. Any technician in the world can open that door and immediately know what forces they're looking at.
So we have our paper canvas spinning, and we have a red pen and a blue pen waiting to drop ink. Let's talk about the physical forces in the pipeline that are actually driving those two pens. I want to look at the red pen first. The differential pressure.
Okay, differential pressure.
Think about a standard garden hose running at full blast in your backyard.
That's a great way to visualize fluid dynamics, yeah.
Right, so if you have water flowing out of that hose and you just jam your thumb halfway over the opening, the water sprays out faster, sure. But more importantly, pressure builds up intensely right behind your thumb, inside the hose. That restriction in your thumb creates a high-pressure zone upstream and a lower-pressure zone downstream once the water escapes past it.
Exactly. And in massive industrial pipelines, that thumb is a specifically machined piece of metal called an orifice plate.
An orifice plate?
Yeah, it's simply an engineered restriction bolted inside the pipe. Because the flow is being forced through a smaller hole, the higher pressure is always going to be on the upstream side, and the lower pressure develops on the downstream side.
Okay, that makes sense.
And the mathematical difference between those two specific points is the differential pressure. As the flow rate of the natural gas increases through that plate, the differential pressure increases right along with it in a very, very predictable way.
Okay, so the orifice plate acts like a thumb on a hose, creating that pressure difference. I get the physics of the pipe itself, but I just can't picture how you physically connect that roaring high-pressure gas pipe to this delicate little glass-windowed cabinet without, blowing the whole thing off the wall.
Right, it seems like a mismatch.
How does the machine actually catch that massive pressure safely to move the delicate red pen?
Well, it requires a really beautiful piece of mechanical translation. There is heavy-duty pipe tubing that runs from both the high-pressure side and the low-pressure side of the orifice plate. These lines run directly into a differential pressure unit, or DPU. This is a rugged, heavy metal bellows system bolted directly to the outside of the recorder enclosure.
Okay, when you say bellows, my mind instantly goes to what a blacksmith uses to stoke a fire. Two sides pumping air.
It is a similar concept, actually, but made of industrial steel and filled with specialized dampening fluid. So the high pressure pushes on one side of the internal bellows, and the low pressure pushes on the other. The bellows basically finds the physical equilibrium between those two forces.
Right.
And as the differential pressure changes, the physical movement of that internal bellows produces a tiny, incredibly exact rotation of a mechanism called the torque tube shaft.
The cork tube shaft.
Yes, this shaft penetrates right through the heavy steel wall of the DPU directly into the delicate recorder cabinet.
Just how much is that metal shaft rotating when the pipeline pressure changes massively? Like, are we talking a full spin?
Oh, not even close. The full range of pressure from absolute zero to maximum produces an approximate 8-degree rotation of that shaft.
Wait, really? Just 8 degrees?
Just 8 degrees.
That is barely a nudge. I mean, you can't even eyeball an 8-degree shift.
No, it is microscopic to the naked eye. But that tiny 8-degree rotation of the torque tube is enough to drive the internal link and lever system, which subsequently sweeps the red differential pen entirely across the chart paper.
That is crazy. Okay, so the red pen tracks the flow rate based on that pressure difference. But here is where I get hung up on the manual.
Oh, where is that?
If the red pen is already telling us the flow rate, the blue static pressure pen feels like overkill. If I know how fast the gas is moving through the pipe, shouldn't I know how much gas I have? Why do we need a second pen just to tell us the static pressure?
Well, it seems redundant until you remember one fundamental law of physics. Gases are highly compressible.
Oh, right. Meaning you can squeeze a massive amount of gas into a very tiny space if you push hard enough.
Exactly. Unlike water or oil, which, generally take up the same volume no matter how hard you push them, the volume of a gas changes dramatically depending on the pressure it is under. Okay,
Yeah.
if you want to calculate the true accurate volume of natural gas moving through that pipeline, which you absolutely must do, because energy companies sell gas by the cubic meter, you have to know the internal line pressure pushing in all directions at that specific moment.
And that's the static pressure.
That overall resting pressure is the static pressure, yes.
So 1,000 cubic feet of gas flowing at a low pressure is a vastly smaller amount of actual burnable fuel than 1,000 cubic feet of gas flowing at an extremely high pressure, even if the flow rate looks identical on the red pen.
You've got it. To accurately bill a customer, you need both numbers.
Okay, that makes perfect sense.
And to measure the static pressure, the Barton 22E uses something called a helical Borden tube element.
Mhm.
If you look at the diagrams in the manual, it resembles a tightly coiled metallic spring or like a spiraled brass trumpet valve.
I saw that. But why build a helix? Why not just use a straight pressure sensor tube?
The secret is in the material length. The coiled helical design allows engineers to pack a much longer length of hollow metal tubing into a very compact space inside the cabinet.
Oh, okay.
As pressure builds inside that hollow coil, it naturally wants to uncoil and straighten out. That extra length drastically increases the mechanical sensitivity of the element.
Which means more movement.
Right. It allows for a much greater physical movement at the very tip of the tube, which translates directly to a highly accurate movement of the blue pen.
It is amazing how every shape, every coil, and every fluid choice is designed for maximum physical sensitivity.
It really is an art form.
But capturing that tiny movement at the tip of a coil or getting an 8-degree rotation from a torque tube, I mean, that's only half the battle. If you just slapped a pen on the end of that tube, the data would be a curved mess. You have to translate a tiny rotational nudge into a perfectly straight, readable line on a flat piece of paper.
Oh, yeah. Opening the inner case of one of these recorders is like looking into the back of a Swiss watch. You are dealing with watchmaker-level precision. The movement of the elements is transferred through a complex geometry of drive arms, range arms, connecting links, and pivot points.
I was looking at the internal schematics in the manual, and there are these specific components labeled 0 and full-scale over-range stops. What are those, and what happens physically if they fail or, get misadjusted?
Well, those stops are physical metal barriers built into the linkages. They're designed to prevent the differential pressure pen from driving entirely off the bottom of the paper chart, so below zero, or flying completely off the top edge past the upper range value during a massive pressure surge.
I assume if a metal pen goes flying off the edge of the paper while being pushed by pipeline pressure, it's not just messy, it physically destroys the instrument.
It severely damages the internal geometry, yes. The delicate linkages would stretch, bend, or bind up entirely. The calibration would be completely ruined. And conversely, if those stops are misadjusted so heavily that they don't let the pen actually reach true zero or the true maximum line on the paper, the machine will just consistently record false data.
It's wild to think about an instrument technician standing out in the freezing mud, wearing heavy winter work gloves, trying to adjust a tiny linkage screw to a fraction of a millimeter, while a massive pipeline literally hums and vibrates beneath their boots.
It is an intensely rigorous profession, honestly.
Mm.
The calibration process they perform ensures those pens move exactly as the math dictates. There are very specific adjustment points detailed in the training manual.
Reading through that calibration section, it feels exactly like tuning a guitar.
Oh, that's a good analogy.
Yeah, you have the link screws, which the text says are for coarse linearity adjustments. You use those to square the linkage at a 50% value of the pressure.
Right, that course adjustment gets the geometry of the mechanical arms aligned dead in the middle of the recording range.
Right, it's like using the big tuning pegs on the headstock of a guitar to get the string close to the right note. That's your coarse adjustment. But to get it perfectly mathematically on pitch, you need the microscopic fine-tuners down on the bridge.
And in the chart recorder, those fine-tuners are the linearity adjust screw, which the technician uses to fix any tiny angularity issues in the arc of the pen's sweep.
Okay.
Then you have the pen zero adjust screw, which allows them to place the pen exactly on the zero line when the pipe is totally depressurized.
And finally, you have the range adjust screw, or for the static pressure blue pen, a specific thumb nut, that adjusts the upper range span, making sure that when the pipe is at exactly 100% of its rated pressure, the pen is laying down ink exactly on the 100% line on the paper.
Exactly. And the manual explicitly highlights a critical step for that thumb nut. First, you loosen the lock screw, make your microscopic fine adjustment, and you absolutely must remember to retighten the lock screw when finished.
Because if you don't,
If a technician forgets that one step, the sheer physical vibration of the gas pipeline will just rattle the nut loose and throw the calibration right back out within hours.
wow. Watchmaker precision bolted directly to a roaring industrial force. So we've built this machine, we've routed the high-pressure gas into the massive steel bellows, we've perfectly calibrated the delicate linkages to translate an 8-degree nudge into a sweeping line of ink. But out in the real world, this isn't just a fascinating science experiment in a vacuum.
No, not at all. If we connect all of these tiny gears and capillaries to the bigger picture, the ink on these charts translates directly into safety, rigid regulatory compliance, and, well, hundreds of millions of dollars. The industrial applications are vast and high stakes.
The manual mentions industrial ovens, which completely surprised me. I was so focused on oil and gas pipelines, I didn't think about manufacturing.
Oh, electronic temperature chart recorders are absolutely critical in heavy manufacturing.
Really? How so?
Well, when massive steel components are joined together during industrial welding, the metal undergoes immense residual stress from the localized heat.
Okay, that makes sense.
To relieve that dangerous stress, the welded components are put into a massive industrial oven. The chart recorder tracks the incredibly slow heating ramps, the sustained holding temperatures, and the meticulously controlled cooling rates.
So it's basically making sure the metal doesn't become brittle.
Exactly. That single paper chart becomes the permanent, physical, legal proof that the metal was treated correctly and will not catastrophically fail under pressure in the real world.
That is incredible. But the bulk of the manual really focuses on remote gas flow measurement, which brings us to the money. This is custody transfer. This is basically the cash register of the energy industry.
It absolutely is.
And to show you just how exact this science is, the manual dives into the intense bureaucratic rules from the Alberta Energy Regulator, the AER, specifically Directive 017.
Right. This is where the theoretical physics and clever engineering meet strict, unyielding legal requirements. The AER leaves absolutely no room for interpretation because the financial stakes are just so high.
For example, the physical valves at the metering tap where the machine actually connects to the pipeline, they must be full port valves, and they have to match the sensing line size exactly.
In the millimeter.
Yeah, the directive mandates a 12.7 millimeter minimum valve for meter runs that are 102 millimeters or larger, and 9.5 millimeters for smaller pipes. A field tech cannot just use whatever spare pipe fittings they happen to have rattling around in the back of their truck.
They absolutely cannot. The geometry must be perfect to ensure pure pressure transmission. The AER also explicitly outlaws the sharing of metering taps by multiple differential pressure devices if it causes increased measurement uncertainty.
Wait, why would a company want to share a tap in the first place? Just to save a few hours of labor drilling another hole in the pipe?
To save time, to save hardware costs, and frankly, to minimize penetrations into a high-pressure line. Every hole is a potential leak.
True.
But the AER forbids it. because shared fluid dynamics cause two very specific, very problematic chart errors that ruin the data entirely. The first is called painting.
Painting. Okay, I'm picturing a toddler with a brush, which doesn't exactly sound like precision engineering.
It looks exactly like that, actually.
Yeah.
Painting occurs when the measurement pen moves up and down so violently and so rapidly due to shared tap interference or extreme pulsation in the gas flow that there is no visible separation between the traces.
Oh, so it just scribbles over itself.
Right, instead of a delicate readable line, the pen just creates a solid, thick black block of smeared ink on the paper. You cannot audit or extract a specific numerical value from a painted chart. It is useless data.
Wow. And what is the second error the AER is trying to prevent?
Spiking.
What?
This is a drastic fake rise or fall of the pen trace.
A fake rise?
Yeah, if two machines are fighting over the same pressure tap, one machine might cause a suction effect on the other. It looks on the paper like a massive, dangerous pressure surge, but it is a completely artificial spike. That is why the legal directive states a separate set of valve manifolds must be used for every single measurement device.
The physical installation rules dictating how the pipes run through the dirt are just as strict, too. Like, the sensing lines have to be self-draining towards the sensing taps.
Yes, to prevent liquid condensation from getting trapped in the low points of the line. A tiny puddle of water in the capillary tube will instantly disrupt the measurement accuracy of the gas pressure.
And the human beings operating these machines have a rigid, unforgiving checklist, too. The chart operator has to write down the exact on and off times for the chart, accurate to the nearest quarter hour.
Very precise.
Yeah, and if they are using a specific type of chart called a square root chart, they have to specifically note if the meter is set for atmospheric pressure.
The operator must also record the exact orifice plate size written on the metal itself and document the exact time again to the nearest quarter hour if an orifice plate change occurs during maintenance.
Even temperature recording has rules based on shear volume. The manual says flowing gas temperature must be recorded continuously if the well's production is over 16.9 times 10 to the third cubic meters per day.
Right. But if production falls below that specific threshold, the AER only requires the temperature to be recorded weekly. Every single drop of ink, every single turn of a screw is heavily regulated, meticulously documented, and constantly audited.
So what does this all mean for us? We started this conversation by talking about the cloud, about digital sensors and, the abstraction of modern data. In an era where information is increasingly invisible, where it exists only as fleeting electrical impulses on a glass screen, taking the time to understand a mechanical chart recorder is, well, it's an incredibly grounding experience.
It really is. A chart recorder provides a literal, physical paper trail of reality.
Exactly.
It takes the invisible, massive forces that actually power our world, thousands of pounds of gas pressure, rushing fluid flow, intense industrial heat, and forces those elements to pick up a pen and physically sign their name to a piece of paper.
It is elegant, it is robust, and it works perfectly in the harshest environments on Earth, in places where modern digital technology would simply freeze, short out, and die.
And understanding this analog durability raises an important question, especially as we become increasingly aware of the vulnerabilities in our modern digital systems.
Right. I want to leave you with a final thought to mull over. We live in an age characterized by the ever-rising threat of sophisticated cyber attacks, crippling ransomware, and, cascading software glitches in our modern digital infrastructure.
It happens all the time now.
Given how fragile a grid can be, might there be a future where we actually have to revert? Like, could we see a day where we pull these unhackable, purely mechanical, spring-wound analog scribes out of retirement to ensure our most critical energy grids stay secure and functional?
It is a fascinating possibility. Sometimes the absolute most secure data storage system in the world isn't encrypted in the cloud. It is just a drop of ink on a slowly spinning piece of paper.
Think about that the next time you look at a jagged white line on a digital dashboard or, trust a glowing readout on a screen. Sometimes to really know what's happening, you just need a heavy skill box with a red and blue pen. Thanks for listening, and we'll catch you on the next Deep Dive.